Hi, yeah, afternoon, I guess, everyone. So today I want to talk about the importance of radar in helping us to further study the ARTEMIS landing zones. I'm going to focus on the mini-RF instrument on the LRO. I'm also going to talk a little bit about the FSAR instrument, which is operated by our colleagues on Chandrayaan-2. There's a lot of great science that can be done at the lunar poles, in addition to volatile studies. And so I'll just touch at the end there about how we can apply radar to studying tectonics. Okay, so there's a long heritage of using radar to study landing site support. This stems, way back when we first started landing missions on other bodies, and also up to recently, especially with Mars. The last two rovers, Curiosity, M2020, and then also the InSight land as well, all had a radar component to the landing site analysis, including here on the right is Arecibo data, Earth-based data, which even though several kilometers across, you can still see these features highlighted by arrows, which are these lava flows that weren't seen in regular mapping, so kind of buried. Now, what does radar do for you? One, it can quantify surface roughness, obviously really important from hazard. That can give you constraints also on boulders, distributions on the surface and also the subsurface. That's important, right? Because as the descent thrusters can start, the plumes can, remove the upper regolith and can start distributing rocks, which could be a hazard. And also radar reflectivity is very important. Most descent processes involve a radar altimeters to know exactly where you are from the surface. And so if you have a sort of stealthy region, that's going to affect the way you can land safely. So what exactly does radar do? Here's a bit of a cartoon, but in context of the moon, we're going to be looking at wavelengths between 4.2 centimeters up to 24 centimeters. And by utilizing the different wavelengths, you get a different sense on the constraints of the size of the scatterers, the size of the boulders, and also different penetration depths. And so for what we can do on Moon is we can look from scatterers of like sub-centimeters up to tens of centimeters. And then we can also probe down to depths of centimeters down to meters. And then so that gives us a really nice sort of breakdown what's on the structure of the upper regolith. It also gives us information as well in terms of the composition. So you can use the dielectric properties of the regolith. They can sort of tease out sort of volatile components. We can also use the loss properties as well to look at mineralogical components, especially high loss, high titanium mineralogy. So it gives you a lot of information there. And also, of course, PSRs and other polar regions as well. Illumination conditions are a bit crazy. This is an active instrument, and so we provide our own light. So it gives us an advantage there. Okay, the mini-RF instrument. So it's currently on the Lunar Reconnaissance Orbiter. It's hyperpolarized radar system. Why that's important? Polarimetric measurements allow us to make a whole host of sort of daughter products that we can use to sort of tease out information about the near surface of the lunar regolith. It's dual frequency operating at both S and then shorter wavelength X and C band. Unfortunately, about 14 years ago, we lost our transmitter. You'd normally think that's probably pretty critical. But we're able to leverage bistatic measurements instead. What I mean by that, it's kind of an old technique, actually, radar, is you instead transmit from the Earth, bounce off the moon, and then you can receive it in orbit. That still allows us to collect these really nice radar image strips you can see on the right of Imbrium. It also allows us to sort of break down other kind of sort of studies by using the opposition angle or the bistatic angle and looking at the various returns we get that way in order to sort of look at the subsurface and look for potential volatiles that way. So we use initially both Arecibo. Of course, we've also tragically lost that as well. A lot of tragedies involved with mini-RF, but we persist, we carry on. We've also got Goldstone, which we're going to do the X-band transmissions from, and we're also inquiring into using another transmitter in Australia from the Southern Hemisphere, which gives us new perspectives as well. As for the DFSAR on Chandrayaan-2, similar sort of radar system, also hybrid and fully polarized operations, dual frequency. This is using S-band, so complementary with mini-RF, but also gives the long wavelength L-band as well. And they also have flexible CONOPS as well. Okay, so to give you an idea of the sort of data we've got available, here is the South Pole, here are the ARTEMIS landing sites. You can see this is now looking at the monostatic, so this is when we're still actively transmitting and receiving on the spacecraft. You can see they've pretty much got full coverage at S-band, that's the 12.6 centimeter wavelength, and then almost near coverage at the X-band. If we extend this now to the bistatic, these are these like sort of long strips, we can see we've got a good coverage before we lost Arecibo. And then we're continuing to do data collects with the X-band, the shorter wavelength. And so these are different colors related to different extended missions, but These do not include actually the 3 collects we got last week, so we're continuing to add to this to get more data. For DFSAR, they've got near full coverage as well. On the left, this is the circular polarization ratio. That's one of these sort of polymetric products we're talking about. Basically, it's a way to highlight sort of roughness and near surface boulders with warmer colors. Maybe you can make out, it's hard to see, some of the craters there are red because they're like got a lot of boulders and that sort of thing. And then another one example is the fully polymetric decomposition, where we can sort of deconvolve the scattering history as well. We can do this with mini-RF, but it's just an example for DFSAR. And see, they've got great coverage, and they're continuing to record more information on area. And this table here just kind of summarizes the sort of coverage we got per candidate landing site. So well coverage there, and you can see there's also different scales of the pixel size resolution as well. So and this appears in several of our abstracts and things for reference. Okay, so I'm going to talk through just a few of the landing sites to give an example. This is the Malapert Massives. On the left, you have the Lola data. Then you've got mini-RF. Unfortunately, kind of it's a bit messed up some of the graphics here, so it looks a little better than this, a lot better than this, actually, I can promise you, the actual data. But what we've got is the S-band here in the center, and on the right, we've got normalized. What I mean by that is that the isolation incidence angle, sorry, obviously is has an effect on the scattering. And so when you have topography, if it's flat, that's one thing, but when you have these sort of slopes that both posing away and towards the receiver, you can really affect what you can, the sort of data you can record. And so one of our colleague, Caleb Facets, what he's been able to do is go through all the data and normalize it for local topography using the high resolution topographic data we've got per pixel. And this gives you a much better indication of what's going on, which is a bit blurred out on this particular thing here, but helps you to make out what's actually due to scattering and roughness and boulder collections rather than just these sort of insulation effects. And so we can stretch that out here as well to really emphasize some of these, well, you've got these small craters, these little red dots, which would be areas that would be rough, but also may be areas that you can get rock samples as well. So useful there. We can look now, we can also add in the DFSAR L-band that hasn't been corrected for insulation, but you can see the incidence angle, sorry, but you can see that you can also make up some more details, and this is penetrating slightly deeper than the S-band. For Steny Rim A, similar sort of thing, we're looking at a slope here, and then both at the mini-RF and also at the L-band for DFSAR, you can make out the sort of blocky material on the central crater, but you've also got some of this mass wasting products as well coming down this slope here and here, which could be interesting place to take samples and hazards. And now kind of want to sort of end by talking about tectonic studies, and particularly looking at lobate scarps. These are these small scale features. There's an example of one up here. There are several kilometers across. They're found all around the moon. The interpretation is that they're a manifestation of thrust faulting due to the sort of compression of the moon. And so there's been a lot of studies, a lot of them being led by Tom Morris and Smithsonian, but Maria Banks, who's here at this conference, she's also done a lot of fundamental work on these and knows a lot about the subject. And so these are interesting because they're very incredibly young. These really fine sort of morphologies. You see cross-cutting relationships of small impact craters as well, showing that they're very young and kind of currently being formed. So they're an example of an ongoing process on the moon, showing this tectonic activity. So that's really interesting. Based on the idea of the interpretation of being thrust faults is due to the fact of morphology, but also looking at the fact that they have sort of fresh boulder fields and landslides associated with them, suggesting that there's been active seismic activity ongoing. Kind of a challenge to sort of study them in the poles, just due to the fact that most of this has been done with LROC data, and so you've got the challenge due to the lighting conditions. But why do we really care about these from a a landing site point of view and human missions? Well, as I said, it's an example of ongoing process. So by studying them, we can get a better idea of the sort of thermal state of the moon and how it's contracting over time and how it's reacting. The fact that they're a seismic source means that if you have passive seismic stations around the moon, they can be a source of energy, which can be used to sort of trace out other structures. And there's also potential hazards. So recent reanalysis of the passive seismic experiment from the Apollo era has found that if you look at reanalyze the data and you look at the probabilistic space and you've the recentered or repositioned epicenters here, they seem to be in an area where we've got a lot of these lobate scarps, and so there's an argument that those lobate scarps here are responsible for some of the seismicity that was recorded during the polar period. In fact, one of the largest shallow earthquakes could be associated with the lobate scarp, which is found in the Galash landing site here. That was they've a momentum magnitude of about over 5. And so if you do modeling work with that, it suggests that you'd have ground shaking within tens of kilometers of this region. So it could affect not just the area of the scarp itself, but other landing sites as well. And then that could, because of the unconsolidated nature of the regolith in some of these areas, especially we have created slopes in this highland terrain, they could cause landslides and that sort of thing. So it could be, obviously a threat, a future hazard for human activity. Lola track data over the main Galash lobate slope here shows that its kind of morphology is consistent with the other lobate scopes we've seen on the moon. But one of the other diagnostic features would be trying to look for sort of like increase of boulders. There's some evidence of that, but it's tricky just due to the lighting here. And so that's why by applying radar, both with the mini-RF and the DFSAR, we can really study the sort of buried block concentrations. We can find that there's concentrations of blocky material around the crest here, which suggests that there is highly rocky, even though there's this older highland terrain. And that kind of supports the nature that these are active, ongoing, and provides another perspective in which to study them. So I'll finish there, and thanks very much.
Any questions?
Got away with it. Perfect, thank you.